In this video, we're going to talk about the SN2 stereochemistry. SN2 stereochemistry is what we call stereospecific. And what this means is if you put in a single enantiomer, which could also be called enantiopure, or optically pure, and it would be called optically pure because it would give a single, you'd have a single stereoisomer present, and it would be chiral, and you would be able to have the plane polarized light in a polarimeter, and you would get the specific rotation for the molecule. So if we have a single enantiomer starting material, then we're going to get a single enantiomer product. Okay, and the reason for this is when we look at the SN2 reaction, it's helpful to think about, I'm just going to use hydrogen atoms here, so even though those are not chiral, we'll still flip the setup here. So let's say we have this leaving group on this side, and then we have the nucleophile here. So if you look in inner chapter C of Cardi, and you look at the SN2 reaction, what you'll see is that the LUMO for this sp3 hybridized in this case carbon atom, but it could be anything else, will be an antibonding orbital, an sp3 antibonding orbital that's sticking out opposite side of the leaving group. And this LUMO is basically where the nucleophile is going to put its electrons in order to make the new bond. So for that reason, the attack of the nucleophile is always going to be on the opposite side of the leaving group. Okay, so that's going to give us a transition state that looks like this. Kind of trigonal planar, except that the leaving group is leaving from one side and the nucleophile is coming in on the other side. And so this is going to be the transition state. And this has a trigonal bipyramidal geometry, if you remember that from general chemistry. And primarily, this leaving group is going out the opposite side of the nucleophile. And then what we have is an inversion of the tetrahedron. And we call this the inversion product. And then we also, of course, have the leaving group as the byproduct. So this means when you're doing a reaction, you always need to excuse me, put the nucleophile opposite the leaving group. Now, sometimes, like the substrate that I've drawn here, the molecule is achiral and it doesn't matter. But a lot of times it will matter. So just as an example, let's say we have a chloride leaving group. Let's say we have a cyanoanion as our nucleophile, cyanide anion. And so this chloride is going to be a great leaving group. Cyanide is nucleophile only typically. It's not a good base. It is also a strong nucleophile. So here with a secondary substrate, a poor base, we're going to expect SN2. So this is going to come in and attack opposite side in the back of the chloride anion. The chloride anion is going to come out the front. So that means when we draw the product, we're going to put cyanide in the back, and then the hydrogen will have gotten pushed forward. And of course we have chloride as our leaving group. So you're always going to get that inversion stereochemistry only when we're doing SN2. And so this is going to be one of the ways that you can tell that an SN2 reaction was either perhaps the only one or the primary one that occurs. If it's the only one that occurs, you'll only get the inversion product. If it's the primary one that occurs and you have a little bit of SN1, and here I'm talking about how you know if it's SN1 or SN2. When we talk about elimination reactions, those are going to make the new pi bond. So that's going to be a lot more obvious that we have that occurring. But if you had a competition and you had both SN1 and SN2 occurring, the SN1 is going to give you a racemic mixture, both in enantiomers. The SN2 will give you the inversion product. And so since the SN1 is like 50-50 inversion and retention, you're going to end up with a majority inversion product, and that's going to be a sign you'll have this scalemic mixture, and that's going to tell you that it's not purely SN2, but it's also not purely SN1.